So this is a continuation of 1.5. We'll call this 1.5b as in boy. And we're on page 122 looking at example 2. And it says there, using the graph shown below, determine any relative maxima or minima of the function f of x equals yada 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 in the intervals on which the function is increasing or decreasing. Okay, so here's the graph on the middle of page 122. So what we're looking for is the relative maxima and minima, which means is the maxima, minima is basically just plural of maximum and minimum because sometimes it occurs more often. So let's look and see what we've got here. As far as what we're looking for, our maximum value of our function is this right here. That's our maximum value when x is negative 0.082. Our highest point is 2.004. We also have a minimum, which is right here, and our minimum is negative 1.604. Now, notice that the maximum and minimum are the y values. They're the f of x's, you could say. Okay, so notice that the graph starts rising or increasing from left to right, from infinity up to, it looks like negative 0.082. So it's increasing on the interval, and this is not really part of the equation, but it's just something to be aware of. From negative infinity to negative 0.082, and again it's open. And it also increases from this point right here to infinity. So then it will be 4.082 to positive infinity. Again, open interval there. And it decreases from here to here. So it decreases from 0.082 to 4.082. Okay, so when you're showing an increase or a decrease or a constant, you're using the x value. When you're looking for the maxima or the minimum parts of it, you're using how high and how low it is, so therefore you're using your y values. Okay, so let's look at example number 4, bottom of page 123, as far as the storage area is concerned. And I'm going to use the picture in the book on page 124 rather than take a picture, so you're just going to have to look at that and follow along. So the sound shop has 20 feet of dividers with which to set off a rectangular area for the storage of overstock. If a corner of the store is used for the storage area, so we've got this building, and we are going to use 20 feet of dividers to partition off a corner of the store. We have this red line is the 20 feet of the divider that we have. So we have 20 feet. So therefore the length and width, there's two of them. There's one length and one width. They're going to have to add up to be 20 feet. And it says to express the floor area of the storage space as a function of the length of the partition. So that means we're looking for f of x equals something. Well, in this case, we're looking at area. It says express the floor area. So the area of this partition space for storage as a function of the length. So we'll use L as well. The book uses x, so let's use x just so it isn't too confusing, although I would have used L for length. So the area in reference to or as a function of the length. And what we're going to do is we're going to look at how this works. Now you know that area equals length times width. Okay, so if this is the length and this is the width, if we multiply those, that gives us the area that I have scribbled in red. So what if this length were 6, or width was 6, this length would have to be 14, because remember I said it was 20. So we don't know what that length and width is, so we're going to call the length x, and this length we're going to call, or width we're going to call 20 minus x. So it's whatever x is, We know we have 20 of it, so our other side has to be the difference between this length and our 20 feet. So what is area? Area is length times width. So we've got that equals x times 20 minus x, or our area in reference or as a function of length is going to be 20x minus x squared. Okay, so that's what they wanted to do first. They wanted to come up with an equation where the floor area was expressed as a function of length, meaning that when we do that, if we're doing area as a function of length or area as a function of whatever, it's going to be A as a function of x. So it's going to look like that. And then we're just going to look at whatever area equals length times width. Second part of this says find the domain of the function. What are our possibilities of x? X can be really any number bigger than 0, right? But it has to be less than 20, because this length right here can't be any more than 20, because the length of that and the length of that is going to be 20, so we have to add it. It can't be 20 because we do need a length here. It said we are going to make a rectangle. So this has to be less than 20 so that we have a length here, even if it's 1 inch. This then has to be 19 feet 11 inches. So it can be any length we want as long as it's bigger than 0 and less than 20. So that is going to be our domain. Or if we used interval notation, it would be 0 to 20. Open. Okay? And the next part says using the graph shown at the left, so I'm looking back on page 123, the parabola there. Using the graph shown at left, determine the dimensions that maximize the area of the floor. So what I'm looking at on that graph is I'm looking at the maxima, or the maximum height. The maximum height says that if x is 10, y is 100. That's the highest point. So if x is 10, then 20 minus x also has to be 10, so that when you multiply those together, you get 100. What they're saying is, I could have this these dimensions at different. I mean, I could have this x be 5, and then this would be 15. So then the area here would be 75. Well, that's pretty big, but if this were actually 10 by 10, I would get an area of 100. So that's what they're asking for. What is the maximum area I can get out of this 20-foot long piece of divider? Well, 10 by 10 gives me 100. That's the highest. That's the maximum height on the graph on page 123. So that's where they get the answer there of length and width being 20.